Well, so this is the second live session that we are going to conduct today, and I hope that you are benefited sufficiently from the recap one that we had discussed in the previous session. So, whatever we had discussed in the previous session, most of these were related to, in fact, all of these were related to the mixture, the pure substances. Okay, we dealt with everything whatever concerning the pure substances, the estimation of properties, and in fact the definition of fugacity, and before that the definition of your enthalpy, entropy, etc., etc. Now, when we deal with mixtures, say in a single phase, so when we deal with mixtures, what do we have? We have a set of mixing rules and combining rules. We using those mixing and combining rules, we can just find out the total mixture properties, and we had already discussed the set of all mixing and combining rules for different equations of states, for the compressibility factor charts, how you find Z mix from TCM mix and TC mix and PC mix, and so on and so forth, right. And then after that, what we found out is that it is fine as long as we are dealing with the total properties, but when we deal with the properties of the individual constituents in the mixture. Now, there we found out, or rather there it was discussed, that for in a mixture, say of total property M or something, each particular individual constituent exerts some particular influence which is not equal to the molar property of that particular constituent. What I mean to say this, I had mentioned in my class as well. Suppose you have a ethanol water mixture, right. So, I take 50 cc of ethanol and I take 50 cc of water and I mix them. The total volume of the mixture may not be 100 cc. Why? Because once they are mixed, then in that case the contribution which each particular constituent has to the total property, that changes due to the molecular interactions between the different components. So, therefore, what I mean to say is, suppose we have a capital V number of pure substance. Suppose say we have a capital V number of pure substances. So, then in that particular case, we can very well write it down as if we can write it down as, say, capital V, right. So, therefore, if we can write it down as capital V, then in that case, then in that case this capital V, so therefore, if we have capital V, say, right. So, therefore, suppose we have pure water. What is the total volume of the water? Say it is V total, right. And what is the molar volume of this particular water? This is V total by N total, which gives you the molar volume, fine. But if we have, say, a ethanol water mixture or a propanol water mixture, then in that case we find the molar volume of the mixture, say the molar volume of the mixture, V mixture, that is equals to capital V by N, but for each particular component, this V, this is equals to sigma Ni Vi bar. This is not equal to sigma Ni, say, Vi. So, this is something very important for us to remember, that when the different components are in a mixture, then the contributions are manifested as partial molar properties and not as molar properties. So, this is one thing which becomes very unique when you shift from the pure components to the mixtures. When we are having pure components, we have the molar properties. The molar properties into the number of moles gives you the total property of this system. When we have a mixture, then in that case the partial molar properties into the total number, into the moles of that particular constituent, this when summed up, then this gives us the total property of the system. So, therefore, this is something which we need to remember, and once we find out that, see, it is very easy to find out the molar property, right, but it is not so easy to find out the partial molar property of any particular system. And it is very important to find out the partial molar properties. Particularly, it is important to find out the partial molar fugacity of any constituent in the mixture, particularly when the mixture exhibits a two-phase system, and therefore, for the two-phase system to be in equilibrium, the partial molar fugacity has to be equal in both the phases for each and every component. So, therefore, if we have to determine whether two phases are in equilibrium or not, we have to evaluate the partial molar fugacities of each and every component, and in order to find out the partial molar fugacities of each and every component, we find out that this is the equation for finding out. Now, if you look at this equation, we find that in order to find out the partial molar fugacity here, we need to know, we need to have an idea about the partial molar volume, and we need to know the partial molar volumes not only at the pressure of interest, but for every particular pressure right from 0 pressure to the pressure of interest, and this is almost impossible. So, therefore, just to make matters simpler, because partial molar fugacity has to be evaluated for each and every component in each and every phase in order to decide whether the phases are in equilibrium or not. So, therefore, people try to propose a much more simpler way of finding out the partial molar fugacity, and that particular way, that is applicable for, rather that is known as the ideal solution model. And from the ideal solution model, we find it is very easy to find out the partial fugacity of a component I, provided we know the fugacity of the component I in the pure state and the mole fraction of the component, right. And we also had discussed the range of conditions under which the ideal solution model is going to be applicable. So, therefore, what we did, first we found out that when we are dealing with mixtures, it is the partial molar properties which are important, and therefore, we discussed what are the ways of estimating the partial molar properties. The method of intercepts, the graphical method, that was discussed, and definitely we discussed the characteristics of partial molar properties, and then we found out that it is very important to estimate the partial molar fugacity or the partial fugacity of any component in the mixture, because unless we can do it, we cannot decide whether the two components are in equilibrium or not. And we had also discussed why partial fugacity is different from the other partial molar properties, that also we had discussed, and therefore, just to differentiate the fugacity from other partial molar properties. So, what we did, we denoted it by a cap instead of a bar, which we use for any other particular partial molar properties, right. Now, so therefore, after subsequently, in order to find out the fugacity of a component, what we tried to do, we proposed the ideal solution model, and from the ideal solution model we found out that we can find out the fugacity in the gas phase as well as in the liquid phase from these equations, and we also deduced that the pure component fugacity in the gas phase is nothing but the total pressure of the system. The pure component fugacity in the liquid phase is nothing but the saturated vapor pressure of that particular component. And in equilibrium, this and this has to be equal, which gives us, which reduce to the Raoult's law for low to moderate pressure. This equation along with the additional constants were then used to solve all sorts of phase equilibrium problems for binary mixtures. The type of problems we had discussed and how to find out, rather we had taken up different problems, we were given assignments, we had discussed the Txy, Pxy, Xy diagrams based on Raoult's law as we had deduced, and also the additional constants, etc., and we had discussed these things in details. Now, we had considering this, we find where the ideal solution model is applicable. So, other than this, suppose we are working at a higher pressure, suppose the component is not in large excess, for all these particular things we cannot refer to the ideal solution model. So, for that particular case, what we need to do, we find that for such particular cases the model has to be modified with incorporating a gamma. See, whenever we try to do anything in thermodynamics, in fact, in any sort of engineering sciences, what we do, we first define something as ideal gas, PV equals to RT, then gases are not ideal. How to incorporate this particular effect of non-ideality, PV equals to ZRT. In the similar way, for an ideal solution, it is Fi equals to Xi Fi. Moment it is not ideal, we incorporate some particular correction factor gamma I. And so, therefore, and then we go on to solve the different vapor liquid equilibrium problems that we had already discussed. So, therefore, in this particular case, the only problem is we need to estimate gamma I. Now, why did this gamma I come? It came just because the solutions are not ideal. So, therefore, this must be related to the properties which the solution has just because it is not ideal. The properties which the solution would not have had it been ideal, or in other words, it is the deviation of each and every property from its ideal solution value which is termed as the excess property. Similar to the residual properties that we had discussed for the real gases and real gas mixtures. And therefore, next we try to relate the activity coefficient with the excess properties, and we found out that it can be related to the Gibbs free energy in this particular way. So, therefore, in order to find out gamma I, what we need to do is we need to refer to some excess Gibbs free energy model, right. And from this particular excess Gibbs free energy model, we had proposed the simplest possible model, which is the 2 suffix Margulis equation. This is the model which reduces to G by RT, sorry, this is the model which reduces to G by RT equals to 0 for the extreme conditions as expected. And then from here henceforth we started deducing other slightly more difficult models or more realistic models, for example, the Van Laar model, the 3 suffix Margulis model and other models. For this particular course, the 2 suffix Margulis equation, the 3 suffix Margulis equation and the Van Laar model are important, but it is important that you are aware of the other models, so that in case you need them in future, you are in a position to use those models to find out the activity coefficients. And then we found out the extreme form of non-ideality, the formation of azeotropes. What happens during the formation of azeotropes? We find that there is one particular composition where the mixture boils as a constant boiling mixture, or in other words, at the azeotropic point, the vapor and liquid composition of the boiling mixture are the same. This makes life little simpler, because under this condition, this particular composition, it is very easy to find out the gammas. And so, once we can find out gammas here, and then using those particular gammas, we can find out the constants of the excess Gibbs free energy model that you are planning to use, and from there we can find out, or we can generate the Txy, Pxy, Xy plot for the entire range of compositions that you require. Well, after that there was something else which was very important. Once we understood non-ideality, we understood excess properties, we understood the activity coefficients, we find it something very interesting to note that this activity coefficient is a property of the liquid phase. But in order to estimate this, we need the equilibrium relations of the vapor liquid in equilibrium. So, therefore, we need vapor phase properties and liquid phase properties to find out gamma. Mostly whatever models that have been proposed, all of these are empirical models, and therefore, these models are developed based on a large number of data which have been collected, experimental data, and the empirical correlation is proposed based on some common sense intuition, etc. It is very important to find out whether the models which you are going to use are thermodynamically consistent or not, and the Gibbs-Duhem equation is generally used to find out the thermodynamic consistency. Usually for binary mixtures, this is the equation. So, therefore, the area test for finding out the thermodynamic consistency has also been discussed in the class. Well, after that, so long first we discussed pure substances, then we discussed mixtures, and then we discussed mixtures in two different phases, and but till now we were discussing the solutions which are completely miscible in all proportions. That means, if you start with a very small amount of A and large amount of B, A and B form a solution. If you start from the other extreme also, you find that they form a solution. It is a single phase liquid in equilibrium with a single phase vapor. But there are several substances we encountered in practice where over a particular range of a composition or over the entire range of the composition, the two liquid phases are not miscible with one another and they form an immiscible pair. Say for example, in this particular case, this is the zone of immiscibility. Why does this happen? Because under this condition we find the Gibbs free energy of the mixture is much higher as compared to the Gibbs free energy of the two particular liquid solutions when they are separated. If you mix them, the Gibbs free energy of mixing is greater than 0. And as we all know that for a spontaneous process to occur, the Gibbs free energy of mixing has to be less than 0. So, therefore, under that condition we have partially miscible solutions or partially miscible liquid mixtures, and when the range of immiscibility is very high, we say that they are almost completely immiscible. Then, so what we did, the next thing we discussed the TXY and the PXY diagrams of partially miscible substances and completely immiscible substances. Quite naturally, completely immiscible are simpler. Partially miscible, we find that there is a range of immiscibility which is shown in this particular case, or rather which is bounded by A, B and E, D. So, therefore, beyond this the two liquid solutions are miscible, again beyond this the two liquid solutions are miscible, and within this particular zone they are immiscible, and we find the TXY diagrams for different particular compositions, and we find there is one critical composition which when we start cooling the vapor composition from 3, we come down to one particular point where the first drop of liquid appears, and that is an immiscible mixture of L1 and L2. If we start with any other vapor composition, we find that initially when we start cooling it, we enter into a liquid zone which is miscible. If we keep on cooling further, then beyond this line BD, the single phase liquid separates into two liquid zones. This is also true for higher vapor compositions higher than this particular critical point. Well, after that what we did, after that, after we finished discussing this, and then we discussed a little amount of the retrograde condensation. This is also another very interesting phenomena. We found out that, rather we discussed that the critical point for a single component system, that is the highest temperature and pressure under which the liquid and vapor can coexist in equilibrium. But for a mixture, the critical point may not be the highest point. The highest temperature point and the highest pressure point, they are often known as the max Konden bar and the max Konden points. So, therefore, we had discussed several particular situations where the critical point, the max Konden bar point and the max Konden point, they form a zone, and if the composition lies within that zone, we find several interesting phenomena. So, we had discussed a little about that, and we had ended our course by mentioning that the entire discussions on phase equilibrium was confined to Txy, Xy, where vapor and liquid are in equilibrium. When you study mass transfer, we find that there are a large number of cases where two liquid solutions can be in equilibrium, or rather where a gas and a liquid, it is the mass transfer is governed by the solubility between the gas and the liquid phases. Okay. We will have distillation these discussions relevant to distillation are these Txy, Xy, Pxy plots. We have absorption where the equilibrium is governed by the solubility of the gas in the liquid. Stripping is the reverse. We have adsorption where the equilibrium between the gas solid or the liquid solid are important. We have liquid extraction where the equilibrium between two liquid phases are important. For example, the equilibrium within this particular dome becomes important. So, therefore, with these particular things we had ended the courses. I hope that you had enjoyed this particular course, and we expect that you will be benefited out of it. For any particular additional doubts, clarifications etc., the TAs Mr. Alex Koshi and Ms. Bonusri Samanto will be available to solve your doubts and to interact with you. So, I think we have a few other doubts. I see it is for phi for positive deviation from Raoult's law, the activity coefficient is greater than 1. What is positive deviation from Raoult's law, you tell me? The positive deviation of Raoult's law is that for an ideal solution, what do we have? We have a linear P versus x plot. If we plot the total pressure as a function of x, then it is linear, and when there is a positive deviation from Raoult's law, then the total pressure is greater than that estimated from the ideal solution model. Or in other words, the calculated PT, or rather the estimated PT of the mixture is greater than the calculated PT from the ideal solution model. So, therefore, for this particular case, if we are considering for low to moderate pressures, then this equation reduces to, this equation it reduces to Pi equals to gamma I xi Pi saturated, right. And so, therefore, and we know this Pi is nothing but equal to Yi Pt. So, therefore, what is Pt equals to? This is equals to, suppose it is a binary mixture P1 plus P2. What is P1 and P2 equal to? This is equals to gamma 1 x1 P1 saturated plus gamma 2 x2 P2 saturated. So, therefore, if Pt has to be greater than that estimated from ideal solution model, which is x1 P1 saturated plus x2 P2 saturated, if Pt has to be greater than Pt ideal, then in that case gamma 1 and gamma 2 has to be greater than 0, right. And under such a condition, the mixture it boils at a lower temperature as compared to the pure component mixtures. So, therefore, we find out that for positive deviations from Raoult's law in this particular case, this is possible only when gamma is greater than 1, and for negative deviation from Raoult's law, it is possible only when gamma is less than 1. And these variations have been shown here, you can find it out that for gamma greater than 1 under this particular condition, we find these are the variations of gamma 1, gamma 2. You have to remember that gamma for any component becomes equal to 1 when the mole fraction of that component tends to 1. So, therefore, gamma versus x1 that originates or that starts from 1 where the component is in excess. For positive deviation it is greater than 1 for both cases, for negative deviation it is less than 1. So, therefore, I guess that with this, since there are no other doubts at the moment, so thank you very much, and but keep interacting with us on the portals, and if you have any doubts even after this, we will be happy to solve them or sort them out. So, thank you very much.